Week 11
So
and week 12 both.
both is today. Oh.
Yes, sir.
So any
Sir, in
doubt
the
in that 11 and 12, you can ask.
no, sir. Sir, in the earlier class, you taught something or just
No,
discussion?
just general discussion. General discussion is that.
Okay, sir. So, sir, can you give the summary of week 11?
Okay. So basically, week 11 is based on the FSM, finite state machine. Okay. So basically, what is the FSM? FSM is the model that will be on the basis of state, and on the basis of input, it will be providing me the next state. Like for example, if we say that if we have a 0 0, and if we apply the input 1, so what will be the next state? Maybe it is 0 1, or it is 1 0, or it is 1 1, or maybe it is 0 0. Same. Okay. So basically, it will be providing me the states where it will be going after applying the input. Okay, now this FSM will be classified in two categories. One is the Mealy and one is the Moore machine. Okay, in the Mealy, the output is dependent on current state and current input. That means in which state we are going, it is all dependent on what is the previous state and what we provide the input. Okay, so currently the input that we provide, and previously what is the input of that one, it will be decided that what is your next state. Okay,
Okay.
whereas in the Moore, the output is dependent on current state only. Okay, it is not dependent on input, not dependent on input. Okay, second thing with that, the output change when the state change. If any input is changed, no change in the output. Okay,
Okay, sir.
so in the case of Mealy machine, you can see that we will provide, like we have a three state A, B, C. To go from one state to another state, there are the lots of the method, lots of the way. Okay, so go from A to B, there is the one way is directly we can go A from A to B. Second way is that initially we go from A to C, then we go from C to B. So there are the two ways. Now, in which way we are processing our data, in which way we are going, approaching from A to B, that is all dependent on the input. Okay, if we apply A as a 0 input, we go to the B. If we apply 1 input, we are going to the C. From the C, if we apply the 0 input, we are going B. If we apply a 1 input, we are going to A. Okay, or we can say, if we from C, if we apply the 1 input, we are going to C, or 0 input, we are going to the A. Okay, now from the B, if we apply the 0 input, we go to the C, and if we apply the 1 input, we are going to the A part. So there are the lots of the way, on the basis of input we decide in which state we are going. Okay, now if state is changed, that means output is also changed. If we go from A to B with 0 input, we say that 1 is the output. Or if I say that from A to, if we apply the 1 input from A to C, we say that 1 is the output. Okay, output is possibly 1 for both cases. Either we apply from state A, either we apply the 0 as an input, we go to the B, the output is 1. Or we apply 1 input, we go to the C, and output in this case also 1. Okay, but it is not possible that with A, if I apply the 1 and 1 input, either we go to the B or either we go to the C. Because with any of the input, we go only on the one state. Otherwise, it will be confusing that if we apply a V at a 1, if we apply the 1 input, we go to the B position or we go to the C position. So to avoid the condition, we can say the input will not same for both. Okay, either from 0 we go with the B and 1 we go with the C. Okay, but output should be same, no issue with that. Clear?
Sir, can you explain this once again?
Yeah. The thing is that if I say that I have a state A, okay, now if we apply the 1 input, so it is confusing that if we apply the 1 input and I am only I am having a state, so either I go onto the B or onto the C, because state is same, input is same, but output is B and C, both different state. Similar case I am taking a example is that you are using a vending machine. Okay, you are using the vending machine. You know about the vending machines? Basically, if you see that in malls, we have a one particularly malls or basically restaurant, we have a one machine. If you press a tea, if we press a coffee, so it will be coming out. Okay. Or similarly, if you see that in the most of the places, there are the vending machines is available. When you put the coin, on the basis of that, you select the product and it will be come out. Okay, so this is the vending machine example. Now, for example, I am on a restart position. Okay, I am on a restart position. That means a same station. Now, in that particularly vending machine, there are the 4 product is available of 20 rupees. One is, I say chips, cold drink, water bottle, or chocolate. Now, if I put a coin of 20 rupees, okay, then what are the possibilities that will come out is either it will become chips, cold drink, water bottle, or chocolates. So it is a confusing. If that machine is not asking what you want, it is a confusing that the machine will be giving us the chips, cold drink, water bottle, or chocolate.
Yes.
Okay. The similar situation is that if we have a position and we are providing the input both as a 1 1, so it is not possible that with the input A1 we go to the B state as well as the C state also. So that means if at position A I am having either I apply the 0, we go to the B position. If I am having the 1, as we go to the C position. Or you can see here also. From A to B, if I apply the input 0, it will be the go to the B. And from A to C, if we apply 1 as an input, we go to the C.
Okay, sir. Get it.
Okay. Now in the case of Moore machine, we have a 3 position A, B, C. Okay. Now that particularly is not dependent on input. So what we do in the case of Moore machine, we only mention the input also here. Okay, we mention the input here. Now with A and input 1, we go to the B. So we only mention what is the output. Either the output is 0 or output is 1. So that means this state is fixed. This state is fixed. We are not changing the input. So that means the which state is coming to the next, it is not dependent on the input. It is only dependent on the state. Now what is the possibility of the state? A at with 0, A with 1, B with 0, B with 1, C with 0, and C with 1. So we have a 6 possibilities. That means 6 states are possible. And with respect to 6 states, we are connecting them. Okay, if we say that A0, we say here as A0 also. Okay. Now these two states are different. Why? Because input is 0 and 1. But this state is not dependent on the input. So we mentioned that input is different, so that means state is different. Okay, so this is about the Moore machine. So
Okay,
it
sir.
is only dependent on the state, and according to that state, it will be giving me the output. Clear?
Yes, sir.
Okay. Now, thing is that how we define, or basically what we are going to say. Like for example, I am taking a flip flop, JK flip flop. Okay. We know if we draw a Mealy diagram for JK flip flop, I can say that hmm, for 0 0, 0 1, 1 0, and 1 1. Okay. We have Qn plus 1. What is Qn plus 1? If 0 0, that is Qn. It is 0, it is 1, and it is Qn bar. Clear? This is the truth table.
Yes,
We
sir.
already say that there are 3 types of table. One is the truth table. Second is the excitation table. What is the excitation table? We assume that previous output is also input for us. That is the excitation table. So till the truth table, we have only 2 input. But in the excitation table, we have the 3 input. Okay, because you can see that Qn plus 1 is dependent on Qn. Now, what is the value of Qn plus 1? It will be dependent on the Qn. So Qn is also considered as an input. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, now what is Qn plus 1? If Jk 0 0, that means these two cases. Qn plus 1 is Qn. Qn is 0, that means Qn plus 1 is 0. Okay, when 0 1, it is 0. When 1 0, it is 1. And when 1 1, it is Qn bar. So if Qn is 0, so Qn bar is 1. If it is 1, it is 0. So that is the excitation table. Now, with the third, we are saying that Sorry, that is the characteristics table. Now third one is the excitation table. Now we assume that Qn and Qn plus 1 is the input and J and K is the output. Okay, if we say that 0, 0, so 0, 0 and 0, 0. Two conditions. So J is 0 and K is variable. So I just say that don't care. 0, 1, 0, 1 and 0, 1. J is constant and K is variable. 1, 0 and 1, 1. Okay.
Okay.
Now we have four conditions. 0, 0, 0, 1, 1, 0 and 1, 1. We have four states are defined. Okay. Now, if we are saying with the four states, I just draw a for J. So when the state is 0, 0, we move to 0, 1. Okay, 0, 0, we move to the 0, 1. For this one, the input of J is 0. Okay, from 0, 1 to we go as a 1, 0. And for input of J is 1. Okay, from 1, 0, we go to the 1, 1. And the input for this one is either 0 or 1. So we consider that it is either 0 or 1. Okay, and 1, 1 to it will be go again as 0, 0 when the input is don't care either 0 or 1. Okay, so we create a basically FSM model of that.
Sir, have you wrote that don't care condition in case there?
Yeah, we see that the input conditions is JK 0, 0 to 0, 1. Okay, so we are saying that four states are available 0, 0, 0, 1, 1, 0 and 1, 1. Okay,
Okay, sir.
now with respect to if we go from this to this, we are saying this is the input. Okay, more better clarity when we go for a stage diagram. Okay, so in this way, if with the any flip flop, we can create a FSM model. I just explain a little bit more about that, how we create from the circuit. Okay, now if we have a circuit, we are having one combinational block. With this block, we have a D flip flop, so D, Q, okay, in this D flip flop, we have inputs 1 and input 2. With the output of combination block, we connect a T. Okay, that is the clock. Okay. Here we say it is a present input for that one, and here we say that it is a present output. Okay, so if I have a clock, we have a present input. Just remember the setup and hold violation. So we are changing our data quite before the change in the clock pulse. Now it will be go. Okay, that is the present input. Now we have the current state. I say there are the current states. Now what will be the next state? Okay, if my input is changed, so my next state will be changed when I change the input. If I say my present input is state 1, state 2, so what is my current? It is state 1, state 2. Why? Because when the clock pulse is changed, the clock pulse is changed, the clock pulse is changed, clock pulse is changed. So at the clock pulse, if my input is state 1, so my current is state 1. Okay. For the second clock pulse, my state is second, my present input is state 2. So we are getting the current as a state 2. Now what will be the next? With respect to this one, we are getting my next state. Either it will be the 1 or something else. Either it will be 2 or something else. Okay. So current with respect to present input, my current state is fixed. Okay. So my basically current state will be dependent on the present input. Okay. When the clock pulse is changed, my present input is changed. For example, I just take a little bit changes here. I just do that my current state is changed here. Again, it will be changed. 2, 3, 4. Now my current state, current output is what? 1, and it will be 2. Okay, no change for the 3. 3 is skipped. Why? Because when the current state 3 will be coming, input 3 will be coming, there is no positive edge of the clock. So that means there is no change happens if I change the input. Okay. After that, when the clock pulse is applied, and a positive clock pulse is applied, we are getting a clock 4. So my next state is 4, not a 3. Okay, not a 3. Now, if my current state is 1, 2, and 4, what will be the my next? It will be dependent on the current. Why? Because the current will be going inside to that input. Now this input will become here. So that will be behave as a present input for the next state. Okay, it will be behave as a present input for the next state. And next state is different according to this particularly. So my next state, when this present state will be 1, so my next state is 1. Okay, or if I say the same timing diagram, if I say the same timing diagram, I am not defining about the next. So this 1 will be coming in this clock pulse. Here we are getting the 1 here. Why? Because this 1 will be applied again back to input when the next clock pulse is applied. And when the next clock pulse is applied, because of this 1, we are getting 1 at the next clock pulse. Okay, so we have a next state with same clock pulse. Okay, with same clock pulse. Clear?
Yes, sir.
Now we can implement this FSM based on the flip-flop. Okay, so we have a D flip-flop. It is D, Q, we have one more D flip-flop, D, Q. Now we say that it is a, this is input B. Okay, now from that input we are going feedback to the combination block. And I assume my combination block is the combination of multiple gates. Okay, so we are using any gate that is not defined. I am using the this one. Okay, or I am using the AND gate and this one. So we are using a different combination block, and on the basis of that block, we are getting the output. Now, if I say that for if we go with this diagram, so we have a two inputs for this combination block. So I assume that one input is X. Okay, so I can apply one input here. Along with that, I just provide here, how long I should provide it here, how long I should provide it. Yes. Okay, so that is my one input. Second input, if you see that it will be coming from the output of D flip-flop. So I just use this output feeding back to the input of this one, then input of, sorry, this one. Okay, now the remaining input is required for this, and this. Okay, so I'm taking one more case is I just connect this output here, here, and here. Okay, that me giving the Y that is given me as a D, and that is given me as a D. So this is the DFF, DFF. Okay, and both flip-flop will be connected with clock pulse. Okay, so we create this FSM using this method. Now it will be dependent on, if you see that, if we have a two input state, A and B, so for possible combination is 0, 0, 0, 1, 1, 0, and 1, 1. Because two outputs are there. Okay, two outputs are there, A and B. So on the basis of this one, we are saying that it is a nothing but a representation of QA, QB. Clear? Any doubt?
No, sir.
Y is considered as a present output and X is a present input. So it will be dependent on from 0, 0 to either I go from 0, 1, I go 1, 1, or I go in this one. The possibilities is there. Okay, the possibilities is there. Now only two ways possible. Why two ways possible? Because the input is 1 bit. Okay, input is 1 bit. If you see the diagram, so you can see the input is 1 bit. Okay, one input is there, not a 1 bit. One input is there. Second is the feedback for the combination. Okay, so either one input is available. So the possible is that either the input is 0 or 1 if it is a 1 bit data. So that means from A, we go either the 0, 1, 1, 1, or 1, 0, any two places. Because input is only single input is available, and for the single input, single bit, only one state is two state is possible. Okay. Now the present output, that is function of present input state. Just hold for 1 minute. Yes. Okay, so present output is dependent on present input as well as the state. If you see that where we are getting the present output from this COM block 2, from this COM block. Okay, from this one we are getting a present output. Okay, from this one and this one we are getting a next state. Okay, so I say that this is the 1 and 2. From the second we are getting the output, and if you see the input for second is one is the input X, and second one if you see that A is connected here and this point is connected with B here. So that means my present output is dependent on the present input and the state. Similarly, if I say the next state, where we are getting the next state? With D flip-flop. Okay, with D flip-flop. And from where we are getting the input for D flip-flop? From here and from here. Okay, now if I am talking about this AND gate, so input is one input is goes to this B. Yeah, this B. Okay, and second will be go to the input X, this one. And for the upper one, D input, for the upper one D, we are required X is the input and A, because A is connected at A here and yeah, only here. So that means the next state is also the function of present input and previous state. Okay, present input and previous state. So we can say that this is a Mealy machine. Because this condition will be followed only by the Mealy machines. Any doubt?
No, sir.
Okay. Now, if we can say that my equation, I know that any equation I can get, like for example, I am getting that an plus 1 is equal to an x plus bn bar x, and bn plus 1 is bn x plus an bar x. And what is the output y? An plus bn bar times x bar. For example, I am saying that. So the important thing is, what is my an and bn and x, and what is my an plus 1 bn plus 1. Okay, now I am putting the 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now can you calculate the an plus 1 and bn plus 1 and y?
Okay, sir.
0 0.
Sir, can you show the an plus 1? Sir, now can you scroll? Sir, an plus 1 is 0, 1, 0, 0, like 4, 0, then 1, then 0, 1.
0 1 Is it
Yes, sir.
clear? Any doubt? Yes.
No, sir, no doubt.
Now we have the AN and BN. So we are taking 0, 0, 0, 1, 1, 0, and 1. If you see that from 0, 0, if I apply input 0, the next state is again same. So if we apply 0 as a input, we are getting the same state, but the output Y is 1. Clear?
Yes, sir.
From 0, 0, if I apply input 1, we are going to the 1, 1. So from 0, 0, if I apply the input 1, I am getting a 1, 1 state, but output is 0. From 0, 1, this is 0, 1. If I apply a input 0, I go to the 0, 0. So go to the 0, 0. If I apply the input 0, and output is also 0. Okay. 0, 1. If I apply the 1 input, I just maintain as a 0, 1 state. So 0, 1, 2, 0, 1. If I apply input 1 and output is 0. Okay. Now 1, 0. I go to the 0. It becomes a 0, 0. So 1, 0. If I apply the 0 as an input, I just go to 0, 0 and output is 1. Now 1, 0. If I apply input 1, so it becomes a 1, 0. So if I apply input 1, I am getting a 1, 0 and the output is 0. Now 1, 1. If I apply a 0 input, so with 1, 1. If I apply a 0 input, I am getting a 1 output. And from 1, 1, if I apply a 1 input, I am getting the next state is 1, 1 and output is also, sorry, input is 1 and output is 0, the last one. So this is my FSM graph. Clear?
Yes, sir.
Now we can implement this one with the help of circuit also. So if I am saying that I have to implement with the D flip-flop, okay. So what we required, we have AN, BN, AN plus 1, BN plus 1. Okay. So AN, BN is 0, 0. 0, 1. We are saying the D and DB. Okay, so for the 4 input, I just create a 16 combinations. Now we draw the excitation table of D flip flop. So D Qn is 0 0 0 1 1 0 1 1. Qn plus 1. If D is 0, we are getting 0. And D is 1, we are getting a 1. Okay, so excitation table, according to the excitation table, if Qn plus 1 and D. So if it is 0 0, we are getting 0, 0 1, we are getting 0, 1 0, we are getting 1, and 1 1, we are getting 1. Oh, sorry. This is 0 1. Yeah. Okay. Now we have a AN. We have a AN plus 1. 0 0. What is the DA? 0. AN 0 0. DA 0. AN 0 1. DA is 0. 0 1 0. 0 0 0. 0 0 0. 0 1 0. 0 1 0. 1 0 1 1 0 1. Okay, so this is my DA. Now similar way I can draw the table for DB. It is 0 0 0 0 1 0 0 0 0 0 1 0. Now 1 0 become 1, 1 1 becomes 1. Again 1 0 become 1, 1 1 becomes 1. 0 0 0 0 0 1 1 1 1. Now can I calculate using the K map? Can I calculate the equation of DA? It is QA, QB, QA plus 1, QB plus 1. So we are getting a, okay, so DA is nothing but QA. And DB, now when the DB is 1, 4, 5, 6, 7, 8, 9. Okay, for DB is, we have two groups. So dB is 2a bar qb plus 2a qb bar. Or we can say it is a qa XOR with qb. Okay. So we have a 2D flip flop. One is the DA, DB. The output is QA, QB. Here is the clock pulse. So for the DA, we required a QA. Okay, and for DB, we required a QA and QB. Take a XOR gate and connected with QB. Okay, so we will design a circuit like that. Anything else you want to ask?
No, sir.
No? Okay. So I'm going to stop sharing here. Thank you. If no doubts.